Um, the way this is gonna work, hopefully, is I'm gonna talk and kind of write on my screen here, kind of like it's a board, it's a blackboard, and I'm gonna record it, and I'm eventually gonna post this to YouTube. I'm kind of using 4 different programs all at the same time to do this, so far it's working. We'll see if it keeps on working. Um, you guys, if you want to try to turn your microphone to ask a question, you can. I'm not sure how that'll work. Otherwise, I think typing in the chat is a good way to wave at me or something like that to say you have a question or something. Um, yeah, I guess that's what I got for now. So the hope is that after class, I'll take the recording and upload it to YouTube, so you'll have that, so you can look over stuff afterwards. Um, the way the class is organized is on Tuesday and Thursday we'll have this. Well, this is bad. Lecture where I talk to you about stuff. I explain to you um, the general ideas of the class and hopefully give you direction for what to do the rest of the week. What you guys ought to be doing on the other days is 2 things. One, I'm going to give you a lab each week. Think of a lab as a guided lesson where I give you a series of steps to follow, and you go through those steps mostly on your own, but ask me for help if you're stuck. And the goal is for you to see the stuff that I do in class, it's only meeting twice a week, in a little more depth, and where you can play around with the computer stuff on your own. The second thing that'll happen that you ought to be doing on these days is the homework. So each week I will also give you a homework to do, which hopefully will be the ideas from lecture and the ideas from lab, where you do something on your own and then you hand that in. So that's the plan. This is the first summer that OWU is doing online classes at all, so nobody's really sure how this is going to work. I have taught online classes in the past at Franklin. They're down in Columbus. So I know a little bit more about how online classes are set up. Um, I think this ought to work. I will tell you guys that a normal summer class, like if you were here in person, is every day, Monday through Friday, for an hour and a half. So you really do need to put in kind of an equivalent amount of time to get what you need to get out of this class. You're not going to do well just coming for these hours on Tuesday and Thursday and then trying to do the homework. You really need to put in time for the labs. You're going to put in time to think about the stuff yourself. You might need to put in time to rewatch some of these lectures, because I'm going to go through a lot of stuff pretty fast to make sure we can get it all in. So do allocate time to do the stuff in this class, and do allocate time to ask for help or look things up if you need to. My plan is to have, I guess, what we would call office hours. I don't know why this is not writing hours. I will probably be here most Monday, Wednesday, Fridays at 11. The time during the week that we would normally have class, but on the days we don't have class, I'll be around. So if you want to set up a chat thing, I'll try to just be logged in at 11 Monday, Wednesday, Friday most days. Sometimes I've got to do other stuff. And then I'll also be around every day from about 2:30 to 4. So I might not necessarily be in here, but if you send me an email about questions, or if you send me an email saying, hey, let's chat, then we can certainly set something like that up. So I'm around. You guys are paying large sums of money to get this class done, and to have me help you. So use me and have me help you. Don't try to do nothing. Don't try to do it all without. If you're confused, it's much harder for me to know if you're confused in an online class because I can't see your faces and I can't see um, whether you're nodding at me when I'm lecturing or that kind of stuff. Um, I guess we turn on the cameras, but nobody wants to see me close up, so I don't want to make you do that. Um, so it's on. It's also very easy when you're in front of a computer to kind of listen to what I'm saying with half an ear while you have some other window open, or you're doing something else, or you're playing with your dog, or whatever. So make sure you are giving this kind of the time and energy that you would give to a regular class. So that's kind of my overview of the course and what's going on and how the online stuff is working. Do you guys have any questions about kind of the logisticy side of things? The textbook, yes. The textbook is called, um, it's in the bookstore, but I thought that's going to help you. This is actually an interesting question. I wonder how they were expecting you to get the book. Because I know I just ordered it through the bookstore. I'm gonna make the Blackboard site live in a little bit. Let me see if I can get you an Amazon link to the book. Um, it's a book by Brookshire. So let me see if I can find it on Amazon. There it is. And then I will, if nothing else, paste it into the chat. Yeah. So that's a link to the book on Amazon. If you can find it online, great. If you can find it used, great. Yeah, I don't. It never actually occurred to me. Usually, I just order books in the bookstore and magic happens. I didn't. I don't. I wonder. I don't know what they were. Did they ever? Did they tell you? Anybody what the books were? I guess not. Right? Huh? Because normally we just go to the bookstore. Huh? Okay. So, if you can find this book soon and for cheap, do it. I would say, though, that I'm going to use the book more as an alternate source of the stuff I'm talking about, in the sense that if you want to see the concepts that I'm explaining in class written down, you can see it in the book. I'm not going to ever make you memorize stuff in the book that I don't do either here or in a lab. I'm not ever going to say your homework is problem 7 from the book and assume you have it. So if it is probably suboptimal but possible to get through the class without the book if you can't get it soon. I still think you should get it. It's not that expensive. But, if the class is so short in time, it's only 5 weeks, that if it takes 4 weeks to get the book, then. So, yeah, sorry about that. I didn't think about that. I'm going to make a list of online problems, and one is, how do they know to get the book? You'd think the bookstore, I don't know. So yeah, because like I said, we're all doing this for the first time, so we're all figuring out how this works, and everybody's kind of doing it in a slightly different way, and we all don't know. Any other questions or problems or anything? I'm going to post the syllabus on the Blackboard site this afternoon. So the Blackboard site's going to go live once today, and it's going to have the syllabus on it, and it's going to have the first lab, and it's going to have the homework. You can I guess I would rather you just emailed me the homeworks when you hand them in, just because I don't like Blackboard and want to minimize my use of it. Blackboard actually has a chat room like I could have used for this, but it sucks. It sucks. Um, so um, so I guess I'd rather just email it to me. That way I know I have it. Email is always a way to contact me. I am very rarely more than 5 minutes away from my email, except when I'm asleep or chasing my kids around. So I guess sending me your stuff in by email is the best way to do it. That's what I would say. So yeah. Anything else? Going once. Going twice. Okay. So today's job is to kind of get you going and thinking about the ideas of what is computer science. This is a course in computer science. The course's name is Understanding Computing. Um, so the idea is that the goal of this class is to kind of teach you in general what computer science is and how computers work and what computer scientists do and that sort of stuff. So normally when I do this face-to-face, I do a little survey and I ask people this question: what is computer science? So just type in whatever you think computer science is. So if I told you I was a computer scientist, what would you think I did? If somebody's majoring in computer science, what kind of job are they going to get? What do you think computer science is in the way that we think, biology is about studying life and things like that? What do you think computer scientists study and computer scientists do? Just type it in the chat if you want. Okay. Coding meaning programming, understanding how computers work. Yeah. Certainly, I get a lot of people telling me, "Hey, you're a computer scientist. How do I install a hard drive and stuff like that?" Sometimes people say stuff like web design, as in I can make web pages. You guys will be doing web pages later in the semester. Sometimes people say stuff like IT, like the kind of stuff the Infosys people do. I'm here to tell you that none of that is true. In the same way that biology is the study of life, and chemistry is the study of matter, and physics is the study of forces and things like that, computer science is the study of what's called algorithms. ALGORITHMS, algorithms, which is a fancy word you've probably never heard of. All it means is an algorithm is a step-by-step solution to a problem. So what computer scientists do is they develop and study and compare and contrast algorithms, and they study and design and compare and contrast step-by-step solutions to problems. And the two big points about this is, first of all, I'll say things to remember. Things to remember, number one, is you don't need a computer to do computer science. You can think about solutions to problems without thinking about computers at all. And two, a program like a computer program, is an algorithm where the steps are written in a language the computer can understand. So let me take these one at a time, okay? You don't need a computer to do computer science. What I mean by that is you've seen algorithms before. You haven't seen the word algorithms necessarily, but you've seen step-by-step solutions to problems. You've seen things like directions to get from here to there. Especially the kind of directions you'd get from MapQuest or Google Maps or someplace like that, where they tell you first turn out of your driveway and then turn right at the light and then go straight for 2 miles and then turn left on this road and then turn right. Those are the steps you follow. The problem is, how do I get from here to there? And the steps are the actual steps you take to get from here to there. You don't need a computer to do that. Another example of an algorithm is a recipe, like to cook something. The problem is, how do I bake a cake? And the actual steps you follow are, first you preheat the oven, then you mix this stuff in a bowl, and then you add the eggs, and you add the flour, and on and on and on, step by step by step by step, until you get to your goal. You've solved the problem, and now you have a cake. Good for you. So the point is, you don't need a computer to do computer science. You don't need a computer to think about algorithms. You guys have thought about algorithms all along. You just haven't used that word. Okay. So here is an example algorithm. It's an actual algorithm. It doesn't need a computer. It's an actual algorithm that you can use in real life to solve a real life problem, without knowing any programming, without knowing any computer. The problem is, two people want to go out to eat, but can't decide where to go. And so the two people are staring at each other and they're saying, I don't care where to go. Why don't you decide where to go? I don't know where I want to go. Why don't you decide where to go? And they're arguing back and forth about where they want to go, and they don't want to decide, and they can't figure it out, and they want the other person to decide, and then until they just decide they want to kill each other because nobody's making a decision. All of this happens to you. It happens to me and my wife all the time. And so we've had quite a few fights about, just decide, damn it, about where to go. So I don't know if this is exactly accurate in saying this is the algorithm that saved my marriage, but it certainly is an algorithm that made my marriage a whole lot easier. Okay? So again, I don't need a computer for this. All I need to do is list out the step-by-step solution to the problem and these steps in the order in which I'm going to take to get to the solution to the problem. Okay? So first step is list out several possible places. Usually about 10 is a good amount. And then step 2 is take turns crossing out places that you don't want to go to. So the idea is if two people cross out places they don't want to go to in order, what you're doing is crossing out the places that you don't want to go to. And then step 3, when one place is left, stop. And the solution is that's the place you're going, because and you're not allowed to complain about it, because if you don't like that place, you should have crossed it out during one of your turns. Okay, so what ends up happening if you do this with somebody, and you should if this problem ever comes up, is you list out a bunch of names of places, of restaurants, and so I don't know. What places are there in town in Delaware? You guys are from campus. You know what Delaware has. So Delaware has things like what? 2 people at the same time. All right. Hamburger Inn. It has Buns. It has, what is Victor's? It has some, okay. You mean Vaqueros? It has Smith if you're feeling sad. Oh, Victor's Taco Shop, okay. All right, what else? Give me a couple more. Mottos. Subway. Chips and Drink. Opa's. Jimmy John's. Domino's. All right, cool. All right, and so now what you do is two people that are trying to decide where to go are trying to decide on a place to go to, and they just take turns crossing stuff out. So I'm not going to make you guys physically do this, but imagine that the first person doesn't like pizza, and so they cross out Domino's, and the second person doesn't want to eat on campus, so they cross out Smith, and then it's back to the first person's turn. And the first person doesn't like Mexicans, so they cross out Victor's. And the second person still doesn't like pizza, so they cross out Amato's. And then you keep taking turns crossing stuff out until there's one place left, and that's the place you're going. Okay? So it's a step-by-step solution to a problem. It took the problem from the beginning and gave you a series of steps to follow that if you follow them all in order one at a time, you will eventually end up with the solution. And it's not a place necessarily that both people wanted to go, but it's certainly a place that neither person can reject because they already had all their chances to reject it. And this actually works in practice, and it actually does stop fights in my family and things like that, and it doesn't need a computer. Okay? So that's the basic idea behind algorithms and how they work. Okay, so one of the things I'm going to give you on the homework, and the homework is also going to be posted on Blackboard. Okay, homework problem number 1. I'll explain this better on the actual sheet that you get. Okay. Design an algorithm to explain how to put on a coat, like and a zipper and stuff. So you have to explain. We're talking to like an alien who doesn't know what a coat is and doesn't really know what the holes are for and things like that. So you have to explain to them what the armholes are, and what left and right is, and where the zipper slot goes, and things like that. So it's really meant to be an exercise in making sure you can explain steps. Okay, we're gonna do a very little bit of programming in this weird language called Scratch. It's about moving a cat around a screen and stuff like that. But it's really just there to show you what programming kind of looks like in a I guess CS class for majors. You do actual programming and you learn how to turn these algorithms into actual programs that you can run. So for now, I just want to make sure you understand the ideas of what an algorithm is and how an algorithm is a series of steps that solves a problem. So cool. Questions on the algorithm stuff? So far, so good. So I am capturing this entire screen, and this entire screen's gonna go to YouTube. Okay, so the log will show up on the side as the video gets played. So yeah, so you should have this whole screen with everybody talking about Hamburger Inn and stuff like that as we go. Yeah. Again, assuming this all works, I am mildly worried that trying to upload an hour-long video to YouTube is gonna get corrupted somehow, but we'll see. That's the plan anyway. So yes, that's my afternoon is figuring that out. All right, any other questions about how this is working and what we're doing so far? Going once, going twice. Okay. All right, so the other thing I wanted to do today to get you ready for this week's lab and stuff is thinking about a little bit about how a computer works. We're going to spend a couple weeks talking about really how it works. Where I want you to be now is realizing that a computer is an electronic device. I'm going to say duh, because hopefully that's obvious. If that's surprising to you, then I don't know what to tell you. But what it means really is that it works by processing electric signals. And the most important part of that is, why can't I extend my page anymore? Do I need a new page? I can't make my screen any longer. So I will instead make a new screen longer. All right. I need to share that window because I'm starting a new page. Whoa, what did I just do? All right. You guys see that? The new page. Okay, cool. All right, so so a computer is an electronic device. Everything inside a computer is electric. Again, I'm going to say duh. The part that's not the duh is this means that electric signals can be either off or on. Okay, so either some part of the computer is getting power or some part of the computer is not getting power. And normally what we do, because computer scientists are lazy and like abbreviations, is abbreviate off as the number 0. No, there is no power coming to it. And on as the number 1, which means yes, you are getting power to it. So why can't I extend this page now? I know why, because it's not at all. Come on. So the reason you care about that is because everything in a computer's memory is stored as electric signals. Or, said slightly differently, as zeros and ones. Okay. If you've ever heard of the term binary, that's where this is coming from. Binary means 2, and the only 2 options are yes and no, and 0 and 1, off and on. If you've heard the word bit, as in bits and bytes, that's where this is coming from. 1 bit is one electrical signal that is either off or on. Okay. A bit is a single stored 0 or 1. So what that means is if a computer needs to do math or counting, it needs to do math or counting all within the realm of zeros and ones. So when a computer counts, they start with 0, and then they go to 1, and then there is no 2. Okay? So instead, what they do is just like an odometer in a car rolls over when it hits the maximum number of digits, it's going to say carry the 1 to the next place and start over. Okay? So that goes to 0, that goes to 1, that goes to 2. Okay? The next number is that, and that goes to 3. The next number, I would have to put a 0 in the first spot because that rolls over, which means I would want to add a 1 to the second spot, but that's already filled up, so that rolls over. And so I'd have to put a 1 there, and that's how I say 4. Okay? So, and then I go to 5, and then I go to 6, and then I go to 7, and so on. Okay? So, this is called, this is called the binary. Whoa, stop, come back. My scrolling is going crazy. Stop scrolling. Stop scrolling. Hey. I don't know what I just did. All right. All right, whatever. This is called the binary or base 2 number system. Called base 2 because there's only 2 numbers, only 2 digits, 0 and 1. Our regular numbers that you're used to thinking about are base 10 because they have 10 possible digits, 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is 10 different things. It works the exact same way as base 10, except we only have 2 digits and we roll over to the next spot after the fact. So when I was going up here and rolling over, okay, I went 0, 1. The next number that has only zeros and ones, if you read that as 10, I guess you can, but it's really the number after 1 is 2, okay? So the reason I'm telling you this is because everything inside a computer is done as a series of bits, and one of the most common things we want to do with those series of bits is interpret them as numbers. Um, so, um, the screen is weird. Okay, so the other term you might have heard of, a byte, is a collection of 8 bits. So why 8? Historical reasons. But a bit is a single 0 or 1. A byte is 8 bits crammed together. And then a kilobyte is 1,000-ish bytes, and a megabyte is a million-ish bytes, and a gigabyte is a billion-ish bytes, and that's where those words come from. Okay, but all of those come from bits down at the lower level. All of those bits are either zeros or ones. Okay, so everything in a computer's memory is a collection of bits. And so that's probably the other. So the two big lessons of the day. One is computer science and the study of algorithms, what an algorithm is. The second one is this, with the corollary that those bits can be interpreted in lots of different ways. So everything in a computer's memory is a collection of bits. Those bits can be interpreted in lots of different ways. And so the trick question that I like to ask a lot is, I'll say, what does this mean? And I'll hand you some collections of zeros and ones. I'll give you 8. That's meant to be a byte that has 8 bits in it, that has 8 zeros or ones. The answer to what does this mean, always is, it depends. Just because you have a series of bits doesn't mean you know what those series of bits are supposed to represent. There's a way to interpret that series of bits as a number. There's a way to interpret those series of bits as a letter, like a letter from A to Z. There's a way to interpret that series of bits as a color, like if a color of a number of something on a screen. There's a way to interpret that series of bits as a location in memory of some other data. There's a way to interpret that series of bits as an instruction or part of one for a computer to do something. Bits can be interpreted in lots of ways. And so the real answer to what does that series of bits mean is you need to tell me how you're going to interpret these bits and what you're going to do with them. Okay, so so one option it's a letter, or the real word is character. The idea is that letters are just stuff between A and Z. Characters include symbols that also could get printed, right? So it turns out that if you want to interpret a series of bits as a character, there exists a standard rule to translate bits to characters. It's called ASCII. It's pronounced ASCII. ASCII. And so what ASCII is, it's an abbreviation that stands for something like the American Standard Code for Information Interchange. But all it is a giant table that maps bit patterns to letters. And probably, I'm looking at the book now, probably the back of the book has an ASCII chart, because most books do. Although this one doesn't seem to tell me about it. I'm just looking in the appendix here. Yep. Appendix 1, ASCII table. And if you look in the ASCII table in the back of the book or online or anywhere else, you'll see, for example, that if I give you this pattern, I get capital A. Why? Because that's what the table tells me. Okay. There's no reason at all ever to memorize the ASCII table. There's no reason at all ever to know the details of how the ASCII table works. What you need to know is that there is such a thing called the ASCII table, and the job of the ASCII table is to translate, to tell you how to interpret bit patterns as characters, letters and digits and symbols and things like that, if that's the way you want to interpret that bit pattern. Okay, so one of the ways seeing bits can depend is if it's interpreted as a letter. Another way that it could depend is that it's a number. Okay, and this is what I was trying to do before with the counting. Okay, here's another. So I guess I want to spend the rest of the time talking about how to do numbery stuff with bits, but I do think I'm going pretty fast. So if you guys want to stop me and slow me down and ask me questions, now's a good time. Going once. Going twice. You guys are still there, right? Or you just okay? It's like I got disconnected and was talking to myself for 20 minutes. Okay, so again, the lab is gonna walk you through this as it goes, but did you guys? I don't know if the schools still do this, but way back in like third grade, you would, at least when I was in school, on our abacuses and stuff, you would give it a number and you talk about the number in terms of the places of the number. This was the ones place. And this is the tens place. And this is the hundreds place. Does that sound familiar? And I did it in school with little blocks, and a little a ones block was one, and a tens. So a one looked like this, and a 10 was a row of a whole bunch of ones, and 100 was a square, and things like that. What they were trying to get you to see was that every spot in a number is there for a reason and there to mean something, right? There's a big difference between this and this and this. It's not enough to just, or even this. They're all 2 zeros and a 1, but where you put the 1 matters, right? So binary numbers, base 2 numbers, work the exact same way. The only difference is I'm only allowed to have zeros and ones in my number. And just like the numbers in the places in regular numbers go up by tens, the one place and a tens place and a hundreds place and a thousands place and a 10,000s place and so on and so on and so on. Here, we still start with the ones place, but the next one goes up to the twos place, and the next one goes up to the fours place, and the next one goes up to the eights place, and so on and so on and so on and so on and so on. Okay, so and the reason they go up by twos instead of by tens is that you had 10 possible digits for every place in a regular number, and you have 2 possible place digits, bits, for every place in a base 2 number. See how the difference is? And so what that means is I can give you an algorithm. See how it's all coming back? For converting binary to decimal. I can give you an algorithm that tells you how to turn a series of bits, and if you want to interpret that series of bits as a decimal number, here's how you do it. Okay. Step 1, put the place values under each bit. And so that would be 1, 2, 4, 8, and so on. So the doubling values of the place. And then step 2, add up all of the places that have ones. And that's it. Okay? So if I hand you something like this, okay, what I do is I kind of mark below it, that's the ones place, that's the twos place, that's the fours place, that's the eights place, that's the 16s place. See how it's going up by twos every time, by just doubling every time? That's the 32s place, and then it goes 64, and the last one is 128. And this can keep going. It just doubles really fast and gets really big really fast. Step 2 says add up all of the places that have ones. That is a 32 and a 16 and an 8 and a 4. You can either do this with a calculator or do this with your head. What I like to do is 16 plus 4 is 20. 32 plus 8 is 40. 20 plus 40 is 60. And so it turns out that this bit pattern here, if you interpret it as a decimal number, is 60. Okay? And that's not a terribly hard, I don't think, algorithm to follow. Okay? So does that make sense? How to go from binary to decimal? Okay. The algorithm, all right, good. I'm going to give you 2 algorithms to go from decimal to binary. And I don't care which one of these you use. The first one I'm going to give you is slow but always works. And then the second one I'm going to give you is kind of a shortcut, but if you screw up the shortcut, you have to back up. So I tend to use the shortcut one, but certainly doing it this way works fine. Start, step one. Start with a decimal number. Step two. Keep dividing by 2 and remember remainders. So remainders is what's left over. Step 3. Stop when your quotient is 1. Remainders are bits. So we're going to keep dividing and stop when your quotient is 0. And the remainders are the bits. So let me walk you through this with I don't know, 14. 14 is a good one. 14 divided by 2 is 7, remainder 0. 7 divided by 2 is 3, remainder 1. 3 divided by 2 goes in once with 1 left over. 1 divided by 2 goes in 0 times with 1 left over. The quotient is 0, so I stop. And now my bits are, and you read them, this is the leftmost and this is the rightmost. So you write them down backwards, and that is your 14. Okay. So that's it'll always work. If you have a big number, it's a lot of dividing, and it's easy to screw up the dividing by 2, but as long as you know how to divide by 2 correctly, you will be good to go. So the other algorithm, what? I don't know why that did such a weird line. You may, let's say, do it wrong. What I'm going to basically try to do is find the largest power of 2 less than or equal my number. A power of 2 is the places in that binary number, 2, 4, 8, 16, 32, so on. I want to find the biggest power of 2 less than my number. Step 2, put a bit, a 1, in that spot. Step 3, subtract that place from number. Step 4, if number not 0, repeat. All right, so here's how this works. Suppose I want to do, I don't know, 95. Okay. I know, and what I would actually do is write out the places. Okay. The biggest place that is less than my number is 64. Okay. The thing you can screw up is if you do this part wrong, you'll mess up the rest of the algorithm. The way you'll know you're wrong, if you pick a number bigger than the number you're trying to subtract, you get something negative. If you pick a number too small, like 32, you'll have what you ought to have left after you subtract is something less than half as big. And if you subtract out something too small to 32, you'll end up with something like 63, which is more than half, so you did it wrong. So then what I do is 95 minus 64 is 31. Okay. What's the biggest place less than 31? It's 16. 31 minus 16 is 15. Whoops. What's the... This is really slow to react, this screen. Okay. What's the biggest place less than 15? It's 8. So I subtract out 8, I'm left with 7. What's the biggest place less than 7? It's 4. I subtract out 4, I'm left with 3. What's the biggest place less than or equal to 3? 2, I'm left with 1. What's the biggest place less than or equal to 1? It's 1. And so every place that I have a 1 is 1, and everything that's not is a 0, and that's the binary number of 95. So I find this way faster. It's less divisioning, and division is slower for people, and it's just subtracting. For numbers like 64, it's super easy. Oops. Because all I do is set it up again and find the biggest place less than or equal to 64. Boom. I don't know what I just did. That's supposed to be a 1. Subtract out the 64, I'm left with 0, and then everything else is zeros. Ta-da! And whereas with the algorithm 1, you'd have to divide and divide and divide and divide and divide and divide and divide. Here, you just have to do it once. I don't care which algorithm you use. I just care that you have a way of thinking about things in binary and decimal back and forth. The lab is going to make you play with a applet. And the applet does this translation for you, and it'll show you the bits. So I just wanted to give you the basic ideas of how to do this and what bits meant, so that you could do the lab, which I will post today. So the lab will be playing around with bits and translations. We'll do more of this kind of stuff on Thursday. And the homework will be due next Tuesday, and it'll be about designing a little simple algorithm for the coat, and then doing some translations of binary numbers and ASCII codes and things like that. So that's all I got for today. Any questions on this stuff so far? I'm going to make the Blackboard. I have another class at 1 o'clock, so I may not be able to get it up before then, but certainly by the end of the day today, the Blackboard site will be available. The recording, however long it takes to upload to YouTube, I'm going to start it right now. I have no idea how long it takes to upload an hour-long recording. The lab will make you go to a web page, do an applet. So you shouldn't have to download anything. You should just have to go to the website and do it there. So I will email you guys with information about when things are up and when things are happening. But hopefully today, the recording will be up, the lab will be up, the homework will be up, the syllabus will be up, and everything will happen well. Cross your fingers. Anything else? If not, thanks for coming. We're going to use this same Hangout room. I think I can keep it up all semester. So I'll try to log into it whenever I'm around. If you want to come chat for office hours, come back here on Thursday at 11 for Thursday's class, and I'll see you then. Yeah, let me know just so I know not to wait for you. But but the recording ought to be up so you can watch it after. Yeah. Thanks. Cool. Thanks for coming, guys. See you guys Thursday.